So what? Well, antisymmetric subspace is one-dimensional, so the matrix H is one-dimensional, so we should be able to do that. I'll take a trace of one-dimensional matrix, just because it's easier for me to do it this way. So I'm only dealing with numbers, but trace of one-dimensional matrix is the only entry in the matrix, so it's no big deal. So one eigenvalue is, I take Hamiltonian, multiply it by the anti-symmetrization operator, take a trace, that gives me eigenvalue. I substitute this guy, it's 1/2 identity minus the flip. What's a trace of Hamiltonian operator? It's sum of these elements. So that's 1/2 2 capital A's plus 2A. That's this term here. What's a trace of H times sigma? We had computed that one as well. The trace is just 2A divided by 2. So that gives us the second term. And we find out that the first eigenvalue simply depends on the oxygen mass. We know that that eigenvalue has to be interpreted as frequency square. So frequency square of the first mode is just this eigenvalue. What's the eigenvector? Well, it's just the projection operator. It's 1 minus sigma. This is identity, this is sigma. The difference is this matrix here. Eigenvector, which involves the oxygens, nothing to do with center of the mass. So this is an eigenmode of this physical system in which carbon in the middle doesn't move and the two oxygens are moving in and out in harmony. So the system breathes like that, and that's one eigenmode. What happens in a symmetric subspace? Remember, that's a two-dimensional system. And we know one thing about the system. Hamiltonian will be 2 by 2 matrix, and its diagonal will be the sum of its eigenvalues. One of them I'll call L plus for symmetric, and the other one I'll call L0. And that's, again, easy calculation. It's a trace of matrix, which we already figured out. This is that, plus the trace of reflection times H, which is just the element H. So this one depends on masses of both particles. So that means it's an eigenmode in which carbon and oxygen will move.